it did occur to me that I probably should have worn this shirt on Monday when I talked about the planets. My Saturn shirt. That's all right, though. Today we get to talk about dwarf planets, which is something I love to talk about because they are some of the most interesting and mysterious objects in our solar system. So before we can talk about dwarf planets, we got to talk about the definition of a planet. And I think we might have mentioned this on Monday. But just as a review, for something to be classified as a planet, according to the International Astronomical Union, it has to meet these three criteria. One, it needs to orbit a star. In our solar system, that means the sun. It's got to be big enough so that it has enough gravity that it forms a spherical shape. So gravity just kind of pulls it to make a sphere. And three, it must be big enough that its gravity has cleared all the other objects of a similar size out of the path of its orbit. And it's this third criteria that dwarf planets tend to fail, because they are much smaller than any of our other planets. Some of them are actually smaller than our own moon. Now, a couple of these we have had a chance to study up close, but a lot of the other dwarf planets we have not had a chance to study up close. And the reason this whole criteria actually came about was due to discovering a dwarf planet that we thought was bigger than Pluto. So when people discovered this object that they thought was bigger than Pluto, they were like, hey, we got another planet. And the scientific community was in an uproar, trying to decide if this new thing should actually be a planet or not, which ultimately led to the Astronomical Union getting together and coming up with a clear set of criteria for what makes a planet. And when they did that, Pluto did not meet this third criteria, like all other dwarf planets, and so got reclassified. Yes, but being reclassified as a dwarf planet doesn't make it less important. It's still a very important Kuiper Belt object for us to study to understand the early solar system. So, thus far, we know of 5 dwarf planets in our solar system: Pluto, Ceres, Makemake, Haumea, and Eris. And we're going to start by talking about Pluto, the most famous and oldest known of the dwarf planets. Now, this right here is a real high-definition image of the surface of Pluto, because Pluto was visited by the New Horizons spacecraft about 6 years ago, July 2015. Pluto's named after the Roman god of the underworld, and it's 1,400 miles wide. So it's not very big. And it's located a whopping 39.5 astronomical units from the sun. So we're talking almost 10 times farther away from the sun than even Neptune is. And it resides in this area that we call the Kuiper Belt. So outside the orbit of Neptune, there is this kind of collection of rocky, icy bodies. And altogether, we call that the Kuiper Belt. And that is where Pluto and most of the other dwarf planets reside. Pluto, we found out after New Horizons visited, actually has 5 moons. The largest moon we've known about for a long time is Charon. And Charon is actually very similar in size to Pluto, to the point where they almost orbit each other, almost like a binary dwarf planet system. And probably one of the coolest features of Pluto is Pluto's heart. There's a heart-shaped glacier on its surface. And it was really amazing when the data first came back from New Horizons, because Pluto was really unlike anything we were expecting. And that's why it's really important to be able to study these objects that are way out in the Kuiper Belt, because we're always learning new things. Next up is Ceres. This right here is also a real high-definition image of the surface of Ceres. So Ceres is named after the Roman goddess of harvests, and it's only 296 miles wide. So we're talking really small, like less than half the size of Pluto. And it's only located 2.8 astronomical units from the sun, because Ceres is the one dwarf planet that isn't a part of the Kuiper belt. It's actually a part of the asteroid belt that exists between Mars and Jupiter. Question? Oh yes, I can go back real quick. Oops. So, 5 moons for Pluto.
Thank you.
You're welcome. But yeah, so Ceres is actually the largest object in the asteroid belt between Mars and Jupiter, and it was originally classified as an asteroid. But when the criteria for planets versus dwarf planets came about, Ceres got reclassified from just a regular asteroid to a dwarf planet. Again, because it's spherical. Where most asteroids do not have like a spherical shape. They're typically like, I don't know, just kind of lumpy or like potato shaped. And Ceres has no moons, and it was also visited by a spacecraft in 2015, the Dawn mission. Now, Ceres was obviously a little bit easier to get to, considering it's only 2.8 astronomical units, as opposed to Pluto's 39.5. But it was also a very interesting one to study, because I don't know if you guys can see it if you're in back, but in a crater like this one, you can see like white patches. And that's true for a lot of the craters on Ceres. And that white is actually water ice. So there was a surprising amount of water ice in the shaded craters of Ceres. Next up is Makemake, which was named after the Rapa Nui god of fertility. This top image here is a real photograph from the Hubble Space Telescope of Makemake. This bottom image is an artist's rendition of what we think it might look like up close. But Makemake is kind of mid-sized. It's bigger than Ceres, but smaller than Pluto, about 888 miles wide. And it's also located in the Kuiper belt, 45.8 AU from the sun. So we're getting insanely far from the sun at this point. And it has one provincial moon. So we think it has a moon, but we haven't collected quite enough data to be able to be like, yes, for sure, it definitely has a moon. But we think it has one moon. Other than that, we don't really know much about Makemake. Other than it maybe has the coolest name of all the dwarf planets. Next up is Haumea. Haumea is named after the Hawaiian goddess of fertility, about the same size as Makemake, 770 miles wide, and it's located in the Kuiper belt, 43 astronomical units from the sun. And we know for a fact that it has 2 moons, and it's got a weird like oval shape. So Haumea actually fails 2 of the qualifications to be a planet. It's also the first Kuiper belt object that we've been able to confirm has rings. So Haumea, although small, has its own like small ring system. Again, this top image right here is a real telescope photograph of Haumea and its 2 moons. And this bottom image is like an artist's rendition of what we think it might look like up close. Lastly, we have Eris. And Eris is really the object that started this whole phenomena of classifying things as dwarf planets. It's named after the Greek goddess of discord and strife, because its discovery is what forced the International Astronomical Union to define what a planet is. It's about the same size as Pluto, about 1,444 miles wide, and it's located 68 astronomical units from the sun. And it has just one really tiny moon. Again, when it was first discovered, Eris was thought to be quite a bit larger than Pluto, And again, originally the people who found it were like, hey, we found a new planet. And it just brought about all kinds of uproar in the astronomical community about what is a planet, does this qualify as a new planet, you know, does that mean Pluto even qualifies as a planet? And ultimately what led to the IAU coming up with its new definition of a planet and Pluto getting reclassified as a dwarf planet. Hence why they named it after the Greek goddess of discord and strife. Yeah.
Can you go back to the Haumea? It was after Haumea.
Oh, Haumea? Yeah, absolutely. Oops, wrong way. There we go, Haumea. Yeah, sometimes I get excited and I go too fast. Like I said, I love the dwarf planets. They're super interesting. And like, again, like 3 of them, because we've never visited, we don't even have like an actual close-up image of. Okay, so here's Eris again. Another interesting fact about Eris is that its orbit is really kind of crazy. Like, it's well outside the plane of the solar system. So like if here's the plane of the solar system, which pretty much all the planets orbit in, Eris's orbit is like at a very clear angle to that plane, which is unusual, and it extends beyond the Kuiper belt. So it's got this crazy angled, super elliptical orbit. This right up here is an actual photograph of Eris and its one moon. And this is an artist's rendition of what we think Eris and its moon, Dysnomia, would look like up close. And you can see that the planets are basically the same size, Eris and Pluto, but the moons are much different, right? So like 2 of Pluto's moons, Nix and Hydra, super tiny. Charon, very large. Dysnomia, kind of small, but not small as Hydra and Nix. But yeah, other than that, we don't know much about the 3 most distant dwarf planets. But hopefully, at some point, we will get to send some kind of like flyby mission to these remote objects in the Kuiper belt. So now we're going to shift gears a little bit and we're going to talk about comets, which will inevitably lead to talking about asteroids and other interplanetary bits of debris. So first off, comets are just icy members of our solar systems that travel in elliptical orbits around the sun. So they're kind of like little chunks of ice and rock that go around the sun. And they're really interesting to study, particularly for astronomers, because we believe that they are some of the last objects in the solar system that are made of the same material as the early solar system. So if you want to kind of know what it was like when the planets and everything were just beginning to form in the solar system, you want to study comets. Additionally, there's a lot of theories that say that a lot of the water on the planets, including our planet, likely came from comet impacts during its early formation. So we're going to talk about the structure of a comet a little bit, and there's kind of 4 main parts to a comet. The first is the nucleus, and it is the core of the comet. And it's just made of frozen ice and gases mixed with, rocky or sometimes metallic solids. A lot of the times, astronomers use the metaphor of a dirty snowball to represent a comet. So you can think of it being mostly like ices, but it's got lots of little specks of dirt and dust and rock in it. And so here on this diagram, this white spot right here in the center, that represents the nucleus of the comet. Out just around the nucleus of the comet is what we call the coma. And the coma is a glowing halo that kind of surrounds the nucleus. And basically what it is as a comet gets close to the sun, those ices start to sublime or turn into a gas, and they expand. And so the coma can be like up to 100,000 kilometers inside. And it tends to glow because of the interactions with the solar wind and the gas particles in the coma. So here on the diagram, this kind of like dark circle around the nucleus, that would be the coma. And then it wouldn't be a comet if we didn't talk about the comet's tails. And all comets have two tails, not just one, two. First is the ion tail. And the ion tail, as the name indicates, is made of ions. So basically charged atoms. So the ultraviolet radiation from the sun tears molecules and atoms into little bits. It starts stripping electrons off of stuff or adding extra electrons, and so you get ions. And those ions, those charged particles, are interacting with the solar wind, and that's what forms the ion tail. So it's these glowing charged particles interacting with each other. And since the ion tail is completely based off the solar wind, it is always a straight tail that is pointed away from the sun. And so in the diagram, this tail right here, the straight one, that is the ion tail. And again, it's always pointing directly away from the sun because it's the solar wind and radiation that is producing it. The dust tail, as the name indicates, is made primarily of dust. So as the comet keeps moving through space, like radiation pressure from the sun, basically really intense sunlight, is striking the core, and it starts pushing dust and little particles off of it. And this forms a curved tail. So you can't really see it in the diagram, but we'll look at some pictures and you'll be able to. But the ion tail is always straight and tends to be more narrow, while the dust tail is going to have a curve to it and is tends to be a little bit wider. So here is kind of a better image. Again, right down here is the coma. And this straight, thin tail is the ion tail. And then this wider, curved one is the dust tail. And so comets kind of have a movement that's a little bit counterintuitive, because we always expect things like when they move on Earth through the air, right? We kind of expect anything trailing behind to just move opposite, be in the opposite direction it's moving. But what you got to remember with comets is that their tails are caused by the charged particles from the solar wind and from radiation pressure. So it's the sun that is blowing ions and dust off the comet. So a comet's tail always has to point away from the sun. And so they end up going back into space tail first. Because again, remember, it's the sun. The sun is always what is blowing ions and dust off the comet. And so the tail will always point away from the sun, no matter where it is in its orbit. Now, eventually, a comet loses material every time it gets close to the sun. So comets don't last forever. Eventually, they will, if they get close enough to the sun, they'll just completely disintegrate and break apart. Or over time, they'll just get smaller and smaller until they're just like a speck of dust. Comets are put into two classifications based on how long their orbital period is. So basically, how long does it take them to make one revolution around the sun? There are short period comets where their orbital period is less than 200 years. So it can be just a couple years, or it can be all the way up to 200. The most famous short period comet is Halley's Comet, that has a 76-year revolution period. And humans have recorded 30 consecutive revolutions, or perihelions, of Halley's Comet. as early as 240 BCE. And that's because it's a very, very bright comet. And all of you guys will have an opportunity to view Halley's Comet the next time it comes around, which I can't remember exactly off the top of my head, but I know I'm going to be old when it comes around, but you guys won't be nearly as old. There's also long period comets. Long periods of comets are anything that has a revolution period longer than 200 years. So it could be like, 300 years, or it could be millions of years that it takes it to go around the sun. A recent example of a long period comet was Comet Neowise that was visible a couple of years ago, I believe. It's got an orbital period of about 7,000 years. And in both of these images, you can see both the ion tail and the dust tail of the comet. Here's Comet Neowise. Its ion tail is kind of bluish, and its dust tail curves out and is whitish. Likewise with Halley's Comet, you've got the whitish, slightly curved dust tail and the bluish, straight ion tail. I had the opportunity of observing Comet Hale-Bopp in, I think that was 1997. So I was very small, but I remember it because my parents set up to do a long exposure photography of the comet. And that was back before we had digital cameras, so you literally had to stand there with a stopwatch and the clicker and time how long to leave the lens cap open. But it was pretty cool. So if you guys ever have the opportunity to see a comet, especially one that's really bright, you should definitely take advantage of that. So origins of comets. So it was kind of curious for scientists because again, we know that ultimately, eventually, comets are gonna, be completely evaporated by the sun or just disintegrated by the sun's gravity. So where are all these comets coming from? Well, that comes up with the model of the Oort cloud. And it basically is a model that tries to explain the origin of comets, where essentially far outside the solar system, so we're talking anywhere from 10 to the 3rd to 10 to the 5th AU. So like, anywhere from 100 to 100,000 astronomical units from the sun is where we think the Oort cloud is. And we think it's just like this big shell of kind of icy bodies. And every once in a while, like a passing star or something else will gravitationally affect some of these icy bodies. And they end up getting sent on a path that will take them towards the sun. And that's where we think new comets come from. So since we've taken the time to talk about comets, it's worthwhile to talk about asteroids and how they're different. Because they can be relatively similar in size, but it's their composition and their shape and appearance that are different. So again, comets are made of ice and dust. You can think about that dirty snowball metaphor. And it always is going to produce a visible tail as it gets near the sun. And most comets have these very long elliptical orbits that take them well beyond Pluto. Again, we said the Oort cloud was probably anywhere from 100 to 100,000 astronomical units away from the sun. Asteroids, on the other hand, are rocky or metallic objects. So they don't really have much in the way of ice. They're either totally rock, totally metal, or they're metal and rock. And they typically have weird lumpy shapes and are a lot of times smaller than dwarf planets. But usually it's their weird shape that doesn't get them classified as a dwarf planet. Again, remember Ceres got classified as a dwarf planet because it's got that nice spherical shape. As you can see here in this image, most asteroids are very lumpy. And they can range in size from anywhere from 1 to like 1,000 kilometers wide. And most of them exist in the asteroid belt between Mars and Jupiter. Unfortunately, movies have done us a disservice of what we think an asteroid belt looks like. So if you think of an asteroid belt in movies, right, you think of all these asteroids close together and the spaceship's got to dodge them all. In reality, though, everything in the asteroid belt is massively spread out. Like, you don't really have to worry about sending a spacecraft through the asteroid belt because it'll probably go straight through without ever running into anything. But that's kind of our key differences between comets and asteroids. Now, there are other smaller types of interplanetary remains, and astronomers use different names for them depending on where they are. So if it's just a kind of small rocky particle that's orbiting the sun in space, we call it a meteoroid. So meteoroids are small little chunks of rock orbiting the sun in space. Now, a lot of times, those meteoroids will get caught by Earth's gravitational pull, and they will start to burn up in our atmosphere. That's what we colloquially call a shooting star. And those visible streaks of light as the meteoroid burns up are called meteors. Meteors are located in the atmosphere. Hence, when we're talking about shooting stars, we're usually telling you to go look for them during a meteor shower, a time when we know there's going to be lots of meteors, lots of little space rocks burning up in the Earth's atmosphere. Now, sometimes those meteors don't completely disintegrate and burn up. Sometimes a chunk of them reaches the Earth. Once it lands on Earth's surface, it's called a meteorite, as in it's right next to you on the Earth. So if it hits Earth's surface, it's called a meteorite. Meteoroids in space, meteors in the atmosphere, and meteorite right next to you on Earth. So this is kind of how I remember them. Again, a meteorite is right next to you. So meteorite right next to you. And then I remember that meteors are related to meteor showers, which means it's got to be something I can see in the atmosphere. Which of course just leaves meteoroids for being the third category. So that's how I kind of use that to remind myself of that. Any other questions about comets or asteroids or dwarf planets? Alrighty, then I just wanted to round up today by reading you guys a passage from Carl Sagan's novel, his book, A Pale Blue Dot. And Carl Sagan, if you don't know who he was a very famous astronomer, particularly well known for working on the Voyager project. And he was really like the first astronomer to introduce astronomy into pop culture. So like you can kind of think of him as like the predecessor of Neil deGrasse Tyson. Without Carl Sagan, we'd never have somebody like Neil deGrasse Tyson. And A Pale Blue Dot is one of his many books where he just kind of talks about his vision for humans' future in space. And there's a really elegant passage in the beginning of it that's very famous. I'm going to kind of read you an extended version of it. The spacecraft was a long way from home, beyond the orbit of the outermost planet and high above the ecliptic plane, which is an imaginary flat surface that we can think of as something like a racetrack, in which the orbits of the planets are mainly confined. The ship was speeding away from the sun at 40,000 miles per hour, but in early February of 1990, it was overtaken by an urgent message from Earth. Obediently, it turned its cameras back toward the now distant planets, slewing its scan platform from one spot in the sky to another. It snapped 60 pictures and stored them in digital form on its tape recorder. Then slowly, in March, April, and May, it radioed the data back to Earth. and I want to actually take a minute to show you the images that it's referring to. Our solar system family portrait here. From this distance, the planets seem only points of light, smeared or unsmeared, even through the high-resolution telescope aboard Voyager. They are like the planets seen with the naked eye from the surface of Earth, luminous dots brighter than most stars. Because of the reflection of sunlight off the spacecraft, the Earth seems to be sitting in a beam of light, as if there were some special significance to this small world. But it's just an accident of geometry and optics. The sun emits its radiation equitably in all directions. Had the picture been taken a little earlier or a little later, there would have been no sunbeam highlighting the Earth. And why that cerulean color? The blue comes partly from the sea, partly from the sky. While water in a glass is transparent, it absorbs slightly more red light than blue. If you have tens of meters of the stuff or more, the red light is absorbed out, and what gets reflected back to space is mainly blue. From this distant vantage point, the Earth might not seem of any particular interest. But for us, it's different. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you've ever heard of, every human being who ever was lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. The Earth is a very small stage in the vast cosmic arena. Think of the rivers of blood spilt by all those generals and emperors so that in glory and triumph, they could become momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturings, our self-imagined self-importance, the delusion that we have some privileged position in the universe, are all challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.